Okay, so we're back. Thank you, everybody. Okay, if you can hear me okay, can you please let me know in the chat? And we'll let some folks stream in. I see we're perfect. Thank you, Stephen. Thanks, Raheem. Appreciate that. Who here has been to any of the MLOps events that we've hosted before? Can you let me know in the chat? Or if it looks like this is the DQ one. Okay, so from earlier today. Interesting. Yeah, so for a lot of people, it sounds like this is a new event, which is great. And I see Yaron's here, so we'll let Yaron come on in a second as well. But yeah, just for a little bit of context, these MLOps events that we host are with the intention of helping democratize a lot of the information that's out there, a lot of the information that's held by some of the bigger FANG companies as well, helping people put models into production in a way that's responsible, that's ethical, that's efficient. I mean, we are really at the stage here in the game where there's so many unknowns that there's not that many principles or methodologies. So it's a really exciting time. It's a time that we, folks are really open to sharing, and we really try and approach this through, the perspective of workshops, technical, high-level technical talks, and a lot of case studies. So I find that a lot of real-world examples, even failure cases, can be really informational, very informative, very helpful. So we really try and focus in on those. And if those of you who are not familiar with the MLOps events that we do, we have the big one in June that we'll do. And I think in 2022, it'll be in person again. And then in November, we have another virtual event, the Toronto Machine Learning Summit. So you can visit it there. We'll have similar talks, similar workshops, I think about 25 workshops and 70 speakers, and some really interesting use cases. And then some other big speakers as well. So we'll have the head of AI from Facebook, Apple, LinkedIn, Twitter, as well as some medium-sized companies as well. And again, we're looking at it through the lens of what information can they provide to our greater community that might help them in their own personal projects. So stay tuned for some of the information there. It will typically go through a committee, so we have it confirmed, and it's by way of what's we deem to be important and what the committee deems to be important. And those are folks working in the fields as well. So that being said, the amount of value that you get from these sessions here are going to be directly proportional to your willingness to ask questions, be vulnerable, even if you're not sure. Everybody, as I said, it's a new sort of area of work that we're all working in. So everybody's on different scales, different levels of understanding and experience. So feel free to ask a lot of questions. We've hosted Yaron in the past. He's absolutely fantastic. I'm going to give him a quick intro in a minute, but you'll see very quickly, he's got a wealth of experience. So we're really grateful for him sharing the work today. So yeah, I hope you enjoy it. Today has been workshops. I believe this is the last one of the day. Tomorrow will be on the Hopin platform. So make sure to check your emails for that. You can visit some of the companies. You can listen certainly to the speakers and ask a lot of questions. You can also see who's attending. So if you have a chance to message somebody, set up a private conversation or chat, that's the goal. We hope that you meet a lot of people. We hope that you make some networking that's valuable and some contacts that will last well beyond the event. That's the goal for us. So I'll see you guys tomorrow as well. But I'm going to be here for this session tonight, or this afternoon, or this evening, wherever it is that you're joining us from. Yaron, if you're there, do you mind joining us here on the screen? And I will transfer it over to you.
Sure.
Thank you so much. You're welcome back.
So thanks for the introduction. I'm Yaron. I'm Yaron. I'm a co-founder and CTO for a company focused on MLOps called Iguazio. We're also developing a bunch of open source frameworks, MLRun, Nuclio, and also contribute to some of the main ones. I come with a long background in systems and data and cloud and so on. And I'll talk about a few things. Let me share my screen. Feel free to ask questions, and you can also reach me after that in LinkedIn. Look me up. I'm trying to be very responsive. Or there's also an MLOps Live Slack channel that we're hosting and has all sorts of, you can interact and ask questions. What we're going to speak about is first the challenges that MLOps is trying to address. And then we're going to go over how to address the different aspects of the building a production solution, anywhere from data engineering parts, the building sort of automated machine learning development pipelines, building the production pipelines sort of with real-time data and so on, addressing the monitoring. We have an hour and a half, so we won't dive very deep into each one of the topics, but we'll give you enough to start with. And again, if you want to dive in more, there's a series of videos that we've published on each one of the topics, and I'll share a link, and you can also reach me out. So without further ado, let's start talking about the challenges. And I'll try and I'll have like 3-4 demos. Let's see what we're gonna manage to squeeze in this hour and a half. But let's start with some of the theory. What are the real challenges in this area? So today, when you develop a model, it's a very interactive process. You extract some data manually. Someone brings you a CSV file or a Parquet file. You run all sorts of analyses, figure out features. You train it in small scale, sometimes using automated frameworks or AutoML. You evaluate the model and so on. It's a very iterative process. At a certain point, when you finish delivering a model, you need to push it to production. Production looks pretty different, and we're gonna dive deeper into how production environment looks like, because data needs to feed from real life sources. It could be databases, streaming data, HTTP endpoints, and so on that need to be gathered. Then you need to prepare the data at scale. You can't just take pandas with a data frame and start manipulating those data sets. Sometimes you use Spark or Flink or other tools. Once you've done that, you need to train on a snapshot of the data, not because data keeps on pouring. So you need to generate a snapshot of the data and run training. Sometimes you want to do it at scale with GPUs and hardware accelerators or at scale. And once you've done that, you need to build model serving pipelines. Models don't serve themselves. You need to do feature engineering for the model serving and monitor the models and so on. So what we typically see is that it's a totally different effort that involves different engineering teams that build the production pipelines. And this wall here represents this effort of doing something and then usually throwing away the notebooks or someone else re-implementing that as Python classes or Java or whatever, and builds a production pipeline. So we're trying to think how to improve that process. Some of the key challenges when we bring something into production in that space is first that we have a siloed working environment. We have DevOps engineers, containers, YAML files, Kubernetes, automation, all of that. We have data engineers using tools like Flink, Kafka, Hadoop, Spark, and so on, building the data SQL, data warehouses, and so on, building the data sets for the online pipelines or the offline pipelines. We have data scientists that use things like Jupyter and Pandas and Scikit-learn and TensorFlow, a different set of tools, different environments, very interactive type of work. And they work on different things, but eventually we need to build one product that encompasses all the components that those guys have built. And we need to integrate it into one solution. And furthermore, maybe a data scientist writes and implements a piece of code. The data engineer may need to take that and expand it to essentially address scale or address performance or security. And you don't want to go back and every time the data scientist makes a change in his environment, redo all the things that the data engineer did on the previous version. So we need to think about the continuous integration and collaborative working environment. The other thing is that the process of moving to production, we're going to go through all those steps, is a very, very long process. It involves taking the code, packaging, testing, securing it, scaling it, tuning it, automation, CI/CD, versioning, and so many things. It usually leads to a very long process to go to production. A major challenge when going to production is when you work with a data set that was gathered for training, maybe someone manually gathered it from different data sources. They did joins and groupings in SQL to prepare this data set. Now you go to production, you don't have the same features because those features were cleaned and manually prepared or obtained after some favors from someone and so on. In production, you have to have exactly the same identical features. So there is a challenge of which is both technological and political of how to get access to all the features that we need for our models, and sometimes we may need to let go of some of the features. And we'll see about some ways of reducing the dependency on features. Finally, we need to make sure that models are accurate. We do some experiments, model accuracy is nice. In reality, the data may differ. We may not have access to the same data. The behavior of the users may change from what we expected them, and models may not be as accurate as we've anticipated. And inaccurate models can lead to a lot of bad situations, customer aggravation, losing money, and so on. We want to make sure that we identify if and when we have accuracy problems, and we want to also mitigate those problems using different techniques. So those are the key challenges that we have when we're operationalizing machine learning. And everyone thinks that, okay, you take a notebook and then you turn it into a product, but that's not really the case. We need to take the code that we've built in data science and turn it into a managed microservice. We need to break the code. That sometimes there is a spaghetti code you'll see in Kaggle that has the data preparation and then the training and then maybe the evaluation, and even the serving sits in the same notebook. Those need to be broken to individual microservices that scale independently, could be deployed independently, and so on. So that's another thing that we'll need to see how to do with automation and not necessarily by manually refactoring notebooks over and over. So we talked about the process in development. What does it mean to build models? So usually it looks something like that. We have some data source, a data lake, a data warehouse, an object storage, S3. We do some interactive data preparation. We do some training and evaluation, and this is the process of building a model. And this is a very small scale, a very smaller part of the overall picture. When we go into production, it looks more like that. Those things that we've seen before are just those. This is a production pipeline. A production pipeline has the different aspects of first generating the data that we can use for the training. And generating the data, again, comes from different sources, whether it's operational databases, data warehouses, streams, APIs. Sometimes we need to develop glue logic to ingest that data. Sometimes the data is real time. We need to use stream processing. Sometimes it's batch. We use tools like Spark or some other programs or commercial products for doing ETL. And then we need to generate the data into different types of data stores, data lakes, in-memory databases, NoSQL, and so on. Now, as we're doing the training pipeline, it may be more than training. First, it needs to be automated. So we can do that again and again. And every time there's a new data set, we need to retrain because there's an accuracy problem. This sort of yellow thing or orange thing needs to be automated. So we need to extract some data set. So we need to do the preparation, the training, evaluation. But also we are starting to add more components into the training pipeline. We may add optimization steps to improve our model behavior or shrink the models in case of deep learning. We want to store the models in some version repository. We want to deploy. Every time we finish, we want to deploy and test the deployment into a production environment. So that's just the training. And the production environment, this is where we may have a model which is being served, but before we need to integrate with some APIs. The request for our model doesn't just come from nowhere. Someone needs to make a request, maybe a JSON structure, a UI front end, etc. Then we need to take that request and add all the features that we had that we need for the model. So that is sort of an enrichment step, and that enrichment step will need to take data from whether it's online data or in-memory databases and so on, and do the serving. And that's a simple serving pipelines. There are way more complicated serving pipelines with ensembles and multiple models, and especially if you're going into deep learning, it can go even more and more complicated. And also beyond the serving, we also need to monitor. So everything that we do, the serving, the data pipelines need to be monitored and analyzed to identify drift or accuracy problems, etc. So each one of those boxes is essentially sort of a microservice that we need to go and develop. Look at how many such microservices we need to go and manage in a production pipeline. So that takes ages, and it requires an army of engineers, not just data scientists, data engineers, DevOps people, software programmers, testing, QA, and so on. This is why in many cases we've seen projects, it takes a year from the minute that someone built a model and tested it to when they can really deploy this full picture. And we're using here some techniques of how to do it in a matter of weeks instead of many months, using a lot of automation. Another challenge when you deal with those type of stacks that you use many different components, and there's a real challenge of integrating all of those different individual components into one cohesive solution. You know, security, logging, monitoring. Each one of those tools has its own way of reporting and troubleshooting and configuration. And so one of the things that we need is also abstraction. So the way that we're addressing it is through an open source project called MLRun. We're going to demonstrate that and how it works, and I'm going to share all the links, and everything I'm demonstrating also is part of the open documentation. So we want to break those. You remember we had those few elements there, you know, all the feature engineering. We had the sort of the development pipelines, we had the real-time pipelines, and the monitoring. So each one of those boxes is essentially being automated using a component in this MLRun stack. And MLRun orchestrates different tools. So potentially the feature engineering may happen in Spark, but MLRun will instruct Spark how to do the actual feature engineering. Or you know, maybe the training will be using TensorFlow, but MLRun will automate the experiment and track the result and take the model and record it and pass it to the serving and so on. So a lot of those things that are very manual in the previous step are automated in this flow. But the general idea is that first, we want to first think about the production pipeline, and from the production pipeline, take things backwards and see how we want to develop the solution. Because in many organizations that I've seen, they're first, you know, building a model using notebooks, etc., and you know, saying, you know what, let's throw it into some serving framework and we're done. And then they get stuck. They don't know how to really build an application, and they waste a lot of energy. So you first think to understand, sort of begin with the end in mind. What do we want to build? We want to build something like that starts by collecting data, building features from that data. We're going to zoom into each one of the components in a minute. Those features that we're going to build, you know, they may also work against some external data store, object store, you know, database, etc. And they will produce a set of features that could be used in 3 different scenarios. We need the features for the development pipeline, so an offline set of features. We need an online set of features for the real-time pipeline, and we need the features for the monitoring. And we'll see why, because when we monitor behavior of the model, we usually compare the data that the model was trained on with the data in serving, and this is really how we know if the model is behaving well or not. So this information is also stored in the feature store because it has the online and offline data, and can also have the comparison, online comparison capabilities. So once we develop the features, we need to train the model. So we'll use a sort of a serverless pipeline that builds all those pipelines that we've seen. And that will produce a model and potentially even deploy the model. Then we use a real-time pipeline, also serverless, that will take and build a set of transformations and the model serving, the feature engineering, etc., and serve the user request, but also emit all the results, all the telemetry data to another component that will essentially monitor all the activities of the model evaluate drift. Potentially can do things like data validation, anomaly detection, and so on. And it feeds back all the data back into the feature store in a way that we can retrain the model later on production data, because all the source of truth becomes the feature store. And this paradigm is not only done by MLRun. You'll see more and more people promoting the concept of feature stores, CI/CD for machine learning. For that, serving pipelines there aren't many solutions, but some are popping, and there are some model monitoring solutions. The advantage of MLRun, it's all sort of glueless integration across all the components, and you have all those components are part of the same open source project. Okay, but it's not really in a vacuum. You have to go and integrate with a different set of tools. So the idea is to also have SDKs and APIs that work with all the different components that are used by the data engineers, data scientists, and ML engineers. So we have BI and data exploration tools that may interact using traditional SQL or JDBC or Pandas. We may have notebooks and IDEs like PyCharm or VS Code, and you may want to take some piece of code and launch it to production with a single API code. There are a bunch of AutoML frameworks out there, including the ones from the cloud providers, SageMaker, Azure ML, Google AI, and so on, that could integrate as part of the pipeline. CI/CD frameworks, GitHub, Actions, Jenkins, and so on, and other tools. So again, you have to know how to work with combination of those in some cases. But the nice thing is that the production pipeline is one. All the other tools are usually interactive, so they're not mission critical. They don't need to be always on. They don't need to be fully automated, and that's a key advantage. So again, we're talking about 4 key components here. Feature store for feature engineering. We're gonna zoom in on that in a second. We have the integration and development and deployment pipeline for the building the machine learning models, taking some code and snapshot of the data and running training, validation, and so on. We have the real-time serving pipelines. We'll show those as well, where again, we can intercept a request from a user or a stream or something, do some processing, data validation, enrichment, potentially serve one or more or multiple models, respond to the user, or do some other actions, and also take all the results back into the model monitoring facility and feature store. And the last piece that we need is the monitoring and retraining framework, where essentially we want to have something seamless that sits underneath that part and collects all the data and monitors and tracks the behavior of the models and can trigger alerts and so on. So those are the 4 components that I'm going to speak about. Now, before we dive further, let's understand, we talked about all those different components here and all those different services. The problem is that developing a service is not just developing a piece of code. It's way more than that. And this is illustrated in that diagram. So we develop a piece of code in using some pandas or using some other tools. And then we need to go through productization efforts. Productization means that first we need to package it, because the code, when we play around with it in a notebook or some IDE, we need to package it as a container that can run on a cluster. So we need to build dependencies and run script and build and unit testing and so on. Then in some cases, we find that the performance is inadequate, or we need to process lots of data, or we have very large models, so we need to think how to distribute the model. So then we're starting to learn all the different mechanisms for distributing data, distributing models, distributing parameters, and so on. So that's an engineering effort. It's not a data science effort per se. Or we run into performance issues, and then we're starting to tune, add GPU support, CUDA drivers, and so on, rapids. We see that our data access is misbehaving, so we move from pandas to maybe databases. We do query tuning, we do caching. We see that Python is single-threaded. We're adding different parallelism technologies and so on to make sure that our model can perform in production, or even our training jobs can perform with a large data set. And finally, because everything is automated and it's not interactive in our ID, we need to add debugging and monitoring and logging, and we're touching production data. We need security. We need everything to be versioned. And one of the challenges, by the way, is that if you have versioning for each independent thing, for the model, for the data center, and they're not synchronized, you don't have one version for the model and the data that is generated for that model, you may have a mismatch and a problem. So we need also to address that. And finally, we need automation. We need CI/CD tools and to build workflows and do things like rolling upgrades and A/B testing. So for every component that we build and start with something working as a prototype, it may take weeks or months to build it. And sometimes we need to collaborate with other members of the team, again, data engineers, DevOps, and so on. So this is why it's very challenging. And one of the things we want to do is automate as much as we can from that process. And the way to do it is using serverless technologies. But before we're diving into what is serverless, let's take a step back. And so, we mentioned we want to build containers. We want to take our workload and put it inside containers. And the dominant technology for that is Docker containers. So what it allows us is to take a piece of code and run it as a process in some computer, but with all the same dependencies that we've built in our development. The same versions of our scikit-learn and pandas and so on will be packaged with our process. And we can run this all on top of something called Kubernetes. And Kubernetes is an open source container orchestration system where it can just run a bunch of containers with some policies around them and schedule them on the cluster. So that's just a few words on Kubernetes. And the way that Kubernetes works is that everything you want to run on the cluster has something called a pod, and those pods have sort of a spec. It's saying run this image and run it maybe with this TCP port and with this scale and so on. So this is could be a tedious effort to take a piece of code and turn it into a container that runs on Kubernetes. And this is why we're seeing an evolution from container to something called functions or serverless functions. If any of you is working with things like Amazon Lambda, etc., so the idea is you don't handle all that containerization effort. You're just providing some high-level definitions of what you want to do, and the containers are built automatically under the hood, with the full telemetry and logging and all those things. So essentially what we want to move is from building containers to essentially taking a piece of code, throwing it to some engine that will build the containers for us. Okay. So before we done this workflow where we had our code, and then we built containers that run on Kubernetes sort of manually, and then we've maybe even by someone else and throw it over the wall, and then we've tested and run our container. Then someone else took our containers and integrated them to a bigger workflow, and potentially with data engineering, with scale and so on. And maybe this guy is called ML engineer and is again a different member of the team. And then we've deployed that workflow, and we want to monitor all the different data, but the guy operationalizing the pipeline doesn't really know what we're monitoring. So he's just monitoring some stuff, but really doesn't have visibility into what we want to achieve, like model accuracy or data analysis and so on. And there's no feedback because what we're monitoring doesn't feed back into our code or into our pipeline. So we want to change this paradigm to something more automated. So with MLRun, the general idea is that you take a piece of code, one click or one command line or API call, it will turn into a managed microservice with all the telemetry and logging and monitoring and everything. And you can just take those microservices and compose a full pipeline, as we're going to see with some use cases, fully automated. And then you don't really need to do anything about monitoring because all the monitoring is built into the framework. So you're just going to open the dashboards and see what's going on. And this monitoring, because it writes back the data and triggers back into the system, it could be used to do things like retraining, fully automated, or feedback to the developer to see the production feature, production information, and tune his model based on that and redo this workflow. So this fully automated process saves a lot of time, a lot of energy, a lot of headaches. And we're going to see how it's done. Okay, and the core concept, again, it's a serverless concept where we're taking the code and we're automatically using solutions that have been developed for the last 5-6 years, essentially fully automatically taking it, making a container, adding all the hooks for the liveliness and auto healing of those containers, adding all the instrumentation to monitor everything happens in the containers, adding resource management to manage its CPU and GPU allocations. All of that is done automatically without a single manual work. Because it's very optimal, then it also increases your performance. It increases the performance of your application, in some cases even 20 times faster, because these containers are built around some real-time technologies and all the aspects of I/O is managed in a parallel way and so on. It makes sure that whatever code you're running is running much higher performance, which eliminates this extra step of tuning and performance optimization. Another interesting aspect is those containers are horizontally scalable. So we talked about one of the challenges is scaling the workload. So the nice thing is that you can run the code, and I'll show you an example with the TensorFlow code, and just change a parameter and it runs it fully scalable. So then you don't need to think about how to scale. You don't need the data engineers to think how to scale, or the ML engineers. You can just change a parameter of scale, and it will make your workload scalable. And every function that you build could be stored in a marketplace and then fetched. This is an example. This is sort of the marketplace where, I want to do some machine learning. I go into some machine learning algorithm, scikit-learn classifier, and I could see a function with all its parameters, etc. This essentially builds AutoML. It's an AutoML function. So I really want to see the code. I can even see how it's implemented. And I could just use it by, copying this line of into my code, and it will essentially run this AutoML function as instead of writing all that code. So this is just as an example. So this serverless concept is going to be used across the board to build all those pipelines and turning our code into something operational. What's unique about those serverless functions, as I mentioned, at first that we can run those functions with set of parameters, data that they're going to use, credentials, and pass them in a secret, confidential way to the runtime parameters. And then every time we run something, it generates results, scalar results like accuracy, operational data like logs, telemetry, and so on, and data. Maybe we're training and we're generating a model, or maybe we're doing data preparation and generating a new feature set that will be used in training. So one of the nice things about it, it creates a sandbox on our function, which essentially auto-records everything that goes in and out. So you guys probably have heard about experiment tracking and all of that. So in MLRun, this is done automatically for you, because we know every time you're launching a code, we know what's being used to run the code, what are the parameters and data, and we know what are the results. So it will automatically log that in a version database, so I can see and go back and forth with my executions, and maybe I want to go back and change the parameters or change the data. It also integrates seamlessly with pipeline engines, and we'll see that as well. So every time I'm running an experiment, there is API and SDK, but the other nice things is that I can essentially control the resources. I mentioned scaling, so I can just determine what is my scaling ratios for every function. I can track every function that runs, whether it's a batch function or a real-time function, and I can just zoom into, remember, it's tracking all my results. So I can just go into specific jobs and see what were the artifacts that were generated by that job, and then just visualize them. Okay, so and there are also, as part of the SDK for the notebook, does exactly the same. So you don't have to use the user interface. Okay, so I'll continue a couple of slides and then I'll show the two demos together. So now that we've talked about all the basic components, the serverless functions, etc. Let's talk about each component in this, out of those 4 components that we discussed. So the first thing is the model development pipeline. This is what everyone does when they start developing models. Is essentially we need to do some data preparation, run some training, potentially test that our model that was generated is accurate or behaves according to our expectations. Another step that we may add is model optimization. We're going to see it in the demos. In machine learning, we may want to reduce the set of features. We may want to choose the best features, etc. So that's whatever we refer to model optimizations. In deep learning, there are different strategies. For example, reducing the layers or compressing data, moving to Onyx models, etc. All sorts of ways of optimizing the models. And once we've done that, we want to deploy a model and test it. Everything that we do, we want to also monitor and track every step in our pipeline, so we know how to go back and we know how to figure out what changed between one execution and another. What usually feeds our system is first a set of code and parameters that are going to be used in our pipelines. And also, I call it a data snapshot because it's not a data. It's essentially when we're thinking about production data may change all the time. You're working against a database transactions of a customer that's doing some activities. Now, in 2 days from now, it's going to have different data. So when we're training, we have to essentially create a view of that data. And this is what's going to feed our training. And also when we're doing retraining, in some other point in time, we may create a window that we snapshot, a window of data, and then feed it into our pipeline. So these are the different steps that we need to cover, and we're going to see that in a second. What we want to do for MLOps is automate that flow, that whenever we change a piece of code or whenever the data changed or we want to retrain on new data set, we want all that flow to run automatically. And we want that the thing to trigger that would be either a manual action or an automated action, like someone just pushed a piece of code into some Git repository and automatically creating a pipeline that will do that. So part of the support that MLRun has is for integration with things like GitLab, GitHub Actions, Kubeflow, etc. That I could define this pipeline of training, data preparation, deployment, and so on. And every time there is a trigger, like someone is creating a pull request, I could just go and launch the full pipeline and even respond back into my pull request, so I can see the progress of my work and also the results. So I can see I changed a piece of code. I can see that it led to different accuracy of the models and other parameters. So then if I change the code again, I know how to compare the different impacts of the code changes. And also, because of the auto telemetry and auto logging, all the information may be logged into other frameworks. Like if you're working with deep learning, it will automatically log all the information to TensorBoard in addition to MLRun's internal tracking systems. So again, this is how we build the pipeline. So with that, let's go over some demo. Okay, so I'll take, hope everyone sees my window. What I'm showing you now is the tutorial that is part of the, so if you go to MLRun.org page and you go to documentation, you see that part of the documentation, we have a getting started tutorial. Okay, so what I'm showing you now is essentially the getting started tutorial. If you install MLRun and there are instructions how to do it, you can just go and download the notebooks or clone the repository and run over those notebooks. Okay. Essentially, the thing about MLRun is that we work with functions. Okay. Now functions and jobs and everything sits in a container called project. So then, if I'm going to MLRun user interface, I can go and into a project screen, and I could see everything that happens within the project, the models, the jobs, the functions, the features, all that belong to a project. So usually what we do is create a project. Once we've done it, let's assume we have a piece of code like this one, okay, which does some data preparation. We want to instrument that code and log the results, or use secrets to the database or whatever. So we need to essentially add something in MLRun called a context. It's not mandatory. You can keep the code as is. And another thing is we're working with data which may be distributed or abstracted away. The data may sit in S3. It may be in a data warehouse. It may be in a local file if I'm debugging things locally. So I don't just pass a URL, because the URL will be, if it's S3, I can't just go and open a file with an S3 URL, okay? Or if it's a database. So what we have in MLRun is a concept of data objects, and data objects has a bunch of methods. It's all, by the way, covered in the documentation with data stores and data items. Again, it supports many different types of backend systems, and have many different methods on those data objects, like download and upload and get and put and view and show. But this is usually what we're using. So this allows us to abstract away the data from where we're running. So if we're running in the notebook, we can just use local file system. If we're running in a cluster, we may use a shared file system or object store or a database. So we essentially rewrite our code to just use data objects and potentially use context. We don't have to, but we can add context. Context allows us to do all sorts of things like obtain secrets, log results, log data, get parameters for our job, and so on. But again, it's optional. We'll see that we don't have to use it in different things. So we're just writing a function. If we want to use notebooks, we usually wrap our function with a marker for starting and ending code, which will teach MLRun when it wants to containerize the job to know where's the real code portion that needs to be containerized. If you're using a Python file, you don't need to do that. You just give the Python file as a source. And then in order to turn my function into something that's a fully managed service, we don't need to do much. We just say code to function. We can give it some different parameters. What is the engine? There are different engines like Job or Spark or Dask or Nuclio and others that are a specialized engine. Usually it matters when you're distributing the workload, or like if you're doing data engineering, you may use Spark, but the base one is called Job. And then we can specify an image or let MLRun build the image for us. But you see a single line of code, I turned this function that I had into a function object, which is essentially a microservice that could be deployed, could be queried, and so on. Now, in order to launch a job on that function object, we usually just do function.run, and we provide parameters. And we can run the job locally in our notebook by just setting local equals true. If we don't set local equals true, it will actually run on the cluster. So you see, the nice thing is that the same code that we write could run locally in my PyCharm or in my Jupyter, or it could run on a distributed cluster with GPUs and CPUs and heavy-duty databases and so on. So all this effort of turning a piece of code into something operational is mapped into a single line of code. And remember, I mentioned the auto tracking. So everything I'm running, you see automatically, I see a track of when it ran and who ran it and what were the input parameters, and some labels like which machine was used and so on, and what were the results and the data with hyperlinks to everything. And if we want to see the full results, we can just go and click and then see the same jobs in the MLRun UI with a lot more context. What was the code that was used for our job? What were the input data, the output data, and so on. I could visualize everything, check the results, logs of the execution, even Kubernetes details if I really want to dive into it. And everything is version. If I run it multiple times, I will essentially see all the different runs, and I could start querying and search between those different jobs. But I didn't need to do anything in my notebook in order to enable that functionality. I just said run, that's it. And this run object, the result of the run, provides me essentially an asynchronous object because the job may actually keep on running. Let's assume it's a half an hour deep learning job. I want to talk to that job using the SDK, so I can just use all those methods. So I can check what's going on with that job. What's the state? It's completed. What are the outputs of the job? I can just see it generates all sorts of version output objects. What are the artifacts? And maybe I want to visualize the artifact as a data frame. So you see the artifact itself may actually be stored in some S3 bucket. I don't need to understand how to go and do IO against S3 bucket or a Google object store or a local file system. I just say, I want the artifact as a data frame. It will go back to my notebook and be visualized, even if the job is running distributed. In order to run the job distributed, I can just turn the flag to false. Let me skip just to that. Just turning the local flag to false, and you see that essentially what it does is also running on a pod on a Kubernetes container resource. So in order to change the run from running on my notebook to running as a container resource, just changing a flag. That's it, or that's the default behavior. And if I want to see the progress of my job, I just click the URL and I'll see the progress of my job. Okay, and again, everything is tracked in the user interface. And I could also schedule jobs if I want, run the same job every day or every few minutes. Okay, and I have a UI for that. So that's the first step of how to build, run a function and run a job on the cluster. Now, when we want to train models, we want the system to track all the information about the models. And if we can do it automatically, it's even better. So let's look at the second step of the tutorial. Again, the first thing I usually do is associate my notebook with the project that I wanted to work. So all the artifacts and everything goes into the project, and I get some also security and access control aspects along with it. And here, essentially, one of the things that we have built into MLRun is a new concept called auto logging. So if we're using a certain framework, let's say scikit-learn or TensorFlow, it will automatically track all the information that TensorFlow or scikit-learn or XGBoost provides. So, and that's done without a lot of code. We just need to add one line of code to whatever we're doing. It's called apply MLRun, which applies all the MLRun optimization and tracking features to our model framework. And if we do that, for example, in scikit-learn, these are all the things that will generate it automatically. We look at the outputs of the job. You'll see that it tracks accuracy and precision and all those things automatically, and generates a bunch of artifacts, including charts and models and test sets, etc. And that could also be controlled, but all of that is generated automatically by simply adding one line of code. So if we have a function that is, for example, a training function, and so we can just write our training function where, again, context is optional. We don't have to use it. We provide it with data object, and we run. This is standard scikit-learn code. There's nothing about it that is MLRun specific. We add this single line, which essentially tells MLRun to start tracking all our behavior. And we see we're using a simple fit, etc. What will happen is that after the fit, MLRun will automatically go and save the model. It will also track all the data assets and all the accuracy and all that in an automated way without all that, just by adding a single line of code. So what we need to do, just like before, we take our training code and we turn it into a function. And then we can just go and run, with a certain data set. Remember the data set we created in the previous notebook, we could just use it as an input to that function. We give it some parameters, and you see it tracked all of those different assets automatically for us. And you can see some of those charts essentially being plotted directly in my notebook. And again, I can see the outputs. I can check the accuracy. I can visualize. Remember, we can visualize data objects. So .show will show that in Jupyter, even though this object may actually be stored in some object store. Again, I could visualize it as a data frame and do all sorts of things with the output of my function. Now, we don't have to write and implement every function. As I mentioned before, we have the marketplace, and the marketplace has many different functions pre-implemented for us. So let's assume I trained my system, and now I want to analyze the behavior of my data, or I did some data preparation. I want to analyze my data set. So there is a function called describe in the marketplace. So function prefix hub is essentially a marketplace. We can also give a URL to functions and so on. And I could check the documentation of that function, and I see it gets a bunch of parameters. And then I could run this describe, this data analysis function on the output of the training, on the training set that was generated by the training function. And this will provide me a lot of different nice charts, like histograms, violin charts, and so on, which analyze my data set. So I didn't have to implement anything special, just use a library function and use that. There is another library function, for example, for testing and evaluating our model. It's called test classifier model. And again, we can import that function, and we can take the result of our training and feed it into this evaluation function. And again, it will do a lot of different analysis on our model and give us information about the accuracy, and again, all sorts of charts will be generated for us. So you see, with minimal amount of work, we actually created a bunch of functions that are fully operational. We can drive them in a minute. You'll see how we put them into a production pipeline. The last thing that we need to build is the real-time pipeline. And for the real-time pipeline, again, we don't sit. It's not a job that gets launched every time we launch a job. It's something that may actually listen on an HTTP endpoint or a stream of Kafka and so on. So here we want to build a class. The class of the model serving has usually by default two methods. One is for loading the model. The other one is for predicting. This is exactly the same way as it's done in other frameworks like KF serving and TensorRT, and even using the same type of class. So we can implement a class for serving. We can actually take a class of serving from the library. We have classes of serving for all the different frameworks, so you don't really need to implement that one. So it's just for sake of example. And you want to serve it as a serving function. What's unique about MLRun, it's not plain serving. You have a concept of serving graphs. So you can build a full pipeline where model serving is just one step of the pipeline. We're going to see it in a second in a more advanced example. But here, we're going to just build a simple graph. So we convert our code into a function. This time we're using the processing engine. It's called serving, and it's not job because it's a real-time serving function using a real-time processing engine. And we can take that function and add the model to that function. We can add the model taken from our previous training. And this way, now we have a serving function with a model. The reason that add the model is a method is because we can essentially add multiple models to the same function. We don't need to build a function for every model. And in order to test that, we can just create a simulator for our function and test with some input data and see the results of our serving graph. In order to deploy that function into a production container that sits on a real-time HTTP endpoint and so on, we just say function deploy. That's it, and we have a production endpoint that listens on our model and responds. We want to test our our model, we can just invoke it, send an HTTP request with the same data and see that we got, result with the output of our model. And all that is also visible through MLRun and Nuclio, which is the real-time engine behind it. We can go and monitor and test from the UI and see all the activities of our model, etc. So this is how we build the full pipeline with the serving. And the last thing that we want to do is create a fully automated flow. So we created a bunch of functions, and those functions now, we want them to automatically launch in a set of pipeline steps every time we do something like change our code or do something else. So here we build a pipeline. So we take our project. Remember, we took all those functions, we built them into a project. We can add all sorts of things into our project, define where the source code resides, etc. So essentially what it builds is sort of a project file that sits in the root of our Git repository. So then every time we want to launch the project, what MLRun will do is look into that, and based on that, it builds the pipeline and executing the pipeline. So we can actually go, after we build the pipeline, we can just go and load the project and run it, or even use a command line. We can automatically run all the different things that we've mentioned using a pipeline, or we can do it even automatically as part of a, like I mentioned, like GitLab or GitHub Actions or Jenkins and so on. You could just launch this pipeline automatically every time you make a code change, and all the outputs of the job will automatically commit into the Git repository. So this is, again, I didn't have any DevOps engineers, any data engineers doing it. It's all built as I'm developing the project. It's already productized. You see, that's the beauty of that. What we're going to use here is a Kubeflow pipeline as an engine for building the pipeline. You don't have to. There is also a built-in local pipeline, as we call it, which has exactly the same semantics. So you can write the same pipeline once and run it locally, assist in debugging and so on, or run it on something called Kubeflow pipeline, which is a distributed workflow automation tool. So I can build a pipeline which has multiple steps. The first step in the pipeline is to run the ingestion. Remember the function from the first notebook. The second step was to run training, the one we used in the second notebook. We do testing using the library function that we imported, and we deploy the model using the function from the third notebook. So we take everything that we developed and debugged interactively. We could just take into a workflow and just run the workflow. And when we run the workflow, it will actually plot with all the results and even an interactive graph that shows the progress of our pipeline. And again, if I'm running it as part of a CI process, this results that will actually go into the user interface. And we can also see the same pipeline in Kubeflow or in MLRun that has a wrapper around the Kubeflow API or in the user interface. So again, I operationalize everything in a few steps, and then I can just go and work against my serving function and see that it actually works. So I built a full pipeline using a set of functions that were taken from my notebook or from my IDE. And then without a lot of work, I made a full machine learning of, pipeline with automation, CI/CD, and all that. So with that, let's move to the more advanced aspects of feature engineering, advanced serving, and so on. Maybe before that, let me show you another example, which I like, is doing the same for deep learning, because machine learning, is more and more understood. Let's take the same concept with deep learning and see why it's, again, so powerful. So this is another example that sits under MLRun for mask detection, like detecting COVID masks with or without COVID masks. And what it's using a TensorFlow model that was developed part of a Kaggle project, I believe. And this code is pure TensorFlow. There's nothing about MLRun here that you see. There's nothing here about MLRun. beside one line that we're going to see in a second. This is building the neural networks and data preparation and all of that. And then we have a function in that notebook called train. That train function has a single instruction for adding MLRun. So there is apply MLRun for Keras. We may give it some parameters, and this will automatically add a lot of magic. It will automatically track all of the activities of our TensorFlow into MLRun and TensorBoard. So all the model behavior, all the tracking will also go to TensorBoard automatically, and we'll do all sorts of optimizations on our model, including addressing auto-scaling capabilities for our training. So this is all using a single line of code. So in order to run our training, we could just, again, do code to function, turn that into a MLRun function, run our training job, this time again locally, and it will just run locally in our notebook. We want to run it as a Kubernetes job. We just change the local to false. This will now run on the Kubernetes cluster. If we want to have GPUs, it's just we need to just change one parameter in the function, and it will automatically run on the cluster with NVIDIA GPUs or something, which will speed up the performance quite significantly. No change for the code, exactly the same code. And if we want to run it distributed as a horizontal distributed job, we need to change the execution engine, something called MPI job, which is a distributed processing engine for deep learning. And when we do that, we also can change some function parameters, like the number of replicas. We want to do 2 containers. We want to have 1 GPU per container, and we can do also other configurations for the execution engine for how we're running the job. Those settings are set at the function object level. And then when I'm going to run the same job, this time using the MPI job execution engine with 2 replicas and GPUs, again, it's going to do exactly the same, just in a distributed way with GPUs. So you see with this one line of code that I instrumented my code in, it automatically turned it into a horizontally scalable solution where everything is tracked. You see in TensorBoard, in this case, or in MLRun. And you could also build pipelines for that deep learning. This is shown here. There's a full pipeline of taking the images and also optimizations around auto optimization the model through Onyx and other layers to make it a much better, much smaller and faster deep learning model. So this is all done automatically for you in the pipeline. Okay, with that, let's go back to discuss the feature engineering and so on. So one of the key things that we see, especially in machine learning projects, but also very critical in deep learning projects. I don't know if I'll get to show you some examples, but in NLP project and even video processing, etc., there are a lot of data transformation steps. But let's start talking about machine learning. So when we do machine learning, we need to essentially take raw data. We do all sorts of manipulations on that data, aggregations, transformations, one-hot encodings, imputing, and so on. And then we get meaningful features. Those meaningful features are what we need for the training, but not just for training. We also need the same features for serving and for governance, because for governance, we need to do all sorts of analysis on the data from production or from training, and potentially also compare those different data sets. And so what we want to do is optimize that and automate this flow, because this is usually 80% of the project is the data engineering part for offline and online analysis. So part of MLRun, there is something called a feature store. I hope people have heard the term already, but feature store is essentially an engine that automates the flow of creating the features, anywhere from connecting to different types of data services, cataloging all those, transforming all those features, cataloging all those features in a version catalog, and then serving them for different APIs, for real-time, for batch, for monitoring, and so on. So this is a feature store, and the feature store interacts with all those applications and users. So on one end, data engineers can go and interact with the feature store to run all sorts of data activities through standard interfaces like pandas, JDBC, and so on. Data scientists can go and develop against the feature store or explore the data in the feature store. When we want to do training, we essentially tell the feature store, give us a snapshot of data and run training directly off of that feature vector. And also the serving will read an online, a real-time feature set and use that for serving. And the model monitoring will also use that for comparisons, but also write back all the results into the feature store so that can be used again for other serving activities or training activities, or for exploration by data scientists or data engineers. So that's a general idea about a feature store. And what the benefits of a feature store is, first, it's a very fast and simple way to productize features. What is the alternative? The alternative is having a lot of data engineers essentially code a lot of SQL queries and stream processing logic, and then thinking how to catalog all of that and how to share those features across different teams. That's a real nightmare. So feature store automates all that process. One critical thing is usually today features are developed once for offline using batch techniques, SQL, etc. And the second time it's re-implemented for real time using stream processing, NoSQL, etc. So a good feature store has one logic that you deploy, and then it will automatically build it for real time and for batch. And when it's building the features become catalog. So you take the features from a catalog and build new applications without any extra effort. So maybe you build some churn prediction application, and then you want to do customer lifetime value. You may need to add another feature, but you already have 10 other features ready for use. So you don't need to redevelop them. And again, we mentioned the Bluelist integration for monitoring and retraining and so on, where feature store becomes very essential for it. And feature stores usually interact with other services like managed services like Spark, etc., for analytics, and managed data services like databases, object store, etc., for storing the actual data. So in MLRun, we have a feature store, which is very advanced. And the idea, again, you can build the transformation graphs of how to turn raw data. Raw data could come from HTTP or a file or a database, and run a set of transformations on it and materialize it in usually two forms, but could have less or more. Usually one for real time in a NoSQL, and then another one for offline in like Parquet files or data warehouses. And once it's doing this transformation graph, it also analyzes the features automatically. So you get all the metadata, all the schemas, all the statistical behavior of every feature that was generated by the feature store. We're going to see in a minute in the notebook how we build that through the SDK in Jupyter, but it could be done in using different tools. Once we build the features, and we may have different feature groups or feature sets, one for users, one for customers, one for product, etc. We may want to build a model that takes multiple features from different feature groups or feature sets. So you can just go into the catalog and select the features and build a vector off of all those features. And then we can take that vector and use it either in a training job, just turning it into a data frame, or in a serving job, or in a real time, we could just fetch the feature vector and use it for scoring. Without, again, no data engineering, no DevOps. This is all doing it once in the feature store and then using it with a single API call. Now, the real challenge today when you're doing feature engineering is lots of SQL. If any of you have built features that, these are features with aggregates and so on, this is a single feature that is used for one of the applications we've looked into. So look at the great challenges of very, very complex. Yes, you can also do it in pandas, but then it's probably not scalable and not something you can automate in production. So people will re-engineer the code into SQL queries run against data warehouses or object store. And that could be very slow, very resource intensive, and it won't work in real time. You can't run a SQL query every time you're doing scoring. So one of the things that MLRun is using, again, using serverless functions, is an automated transformation graph. It has multiple backend engines to implement this transformation graph. It supports Pandas, Dask, Spark, and something called Story, which is a real-time pipeline. And that transformation graph is essentially a set of operators that work on the input data set and eventually materialize. Now, the graph is decoupled from the data source and the data sink. So we can use the same graph for real-time, for offline against different databases. So you just implement that graph, and the graph gets executed on serverless, one or more serverless functions. So we can take a CSV file. By the way, it can also run in the notebook or in the simulator. So we can take a CSV file or a Parquet file or a database as an input, run the graph, and generate a training set in another CSV file or Parquet file. So that's easy, and we could also do it with other tools. But we can also take the same graph and feed it with an HTTP endpoint or a stream like Kafka and produce the same training set without changing the code. But even more sophisticated is that we can take the same graph and feed it from an online data like a stream or a database and generate the real-time serving data set or even time series analysis of the data set, which will be used by model monitoring or dashboards. So all that without changing the code, and all that with maximum performance and maximum operationalization. Again, no DevOps needed. You build the feature, and it supports all those operations without any extra work. Okay. So feature engineering is very critical element, and we're going to see how it fits into production pipelines. But the other critical element is the serving pipeline. So many people think serving pipelines, okay, you know what, I need to build a model endpoint that sits on an HTTP endpoint, and someone brings requests in, and etc. What you'll see is that it's not usually the reality. The reality is that you get some request in some form of a JSON structure. Someone needs to take that JSON structure, validate it, and so on, transform it into some other form, and then maybe that JSON structure includes like a customer ID. We need to take that customer ID and go to the feature store or go to some database and contextualize it, add all the features that belong to that user, the gender, the recent activity of that user, and so on. Once we've done the enrichment, we may want to serve a model, but usually in production, you don't serve a single model. You want to create sometimes ensembles or models that track different windows of time or all sorts of things that will increase the accuracy. In some cases, you have a composable AI where you have like an NLP model with a classification model like XGBoost, all in the same serving pipeline. And at a certain point, we want to drive an action. An action could be respond to the user with some structure, push it to a database, and so on. So we need that, but we also need to track all the responses of our activities into some model monitoring framework. So these are all the different things that we need to do. And again, those systems have to be highly available, auto-scaling to address any workload. They need to be secure, self-healing, and so on. So again, we're going to use serverless functions to build those graphs. So MLRun also has this graph technology, the same one used in the feature store, where I could just go and define a pipeline which I have multiple steps. So it could have a start, again, this is the source, could be HTTP or stream or any other thing. And then it does, like, for example, feature enrichment, some data pre-processing, drive the result into an ensemble with multiple models, then do potentially some post-processing. All this graph could be defined in like a dozen lines of code. We have examples for that in different applications. And then once I've developed this graph of classes, whether these are pre-baked classes or my own custom classes, I can just go and simulate the graph inside my notebook or ID, verify that it behaves exactly as expected, and then I could just say deploy. Deploy will essentially deploy this entire graph with all its functions and microservices, etc., as a live endpoint that sits on an HTTP endpoint or a stream of Kafka and so on. And it will be auto-scaling, self-healing, fully secure, etc. All those things are automatic. So in order to build a full production pipeline, you just need to say deploy. You could even deploy to a separate cluster. You can control, you have maybe one cluster for development and another cluster for deployment. And this deployment operation could also be part of the development pipeline, as we've seen before. Now, those functions, they also have auto tracking built in. So using stream processing. So those serving function will automatically track all the information to an output stream. And we have other functions that do feature analysis on the outputs of the model serving. And based on that, they do alerting or they build dashboards to visualize our model analysis and model drift. You can see the dashboards, whether through Grafana, which is a standard tool. There is a plugin for Grafana for it, or in the MLRun user interface. Okay. So with that, let's go into a use case that takes now the couple of new things we discussed, the feature store and the serving pipelines, and see how we make some good use of that. So we're going to take an example of application of real-time fraud analysis. This is also part of the demo that MLRun has. The first thing we want to do is ingest data. This credit fraud analysis, we have data coming from streams, like account activities, real-time swipe transactions, some data, static data about users. We want to feed all of that data into the feature store. We can have some interactive exploration of that production data using some notebooks if we want. Then automatically we can create a pipeline that takes that data, builds an AutoML pipeline that deploys the model from a new features. We build a feature graph, we build a serving graph that knows how to take real-time features, combine them with the user request, and essentially tells you if it was a fraud or not. All that data is tracked using the model monitoring facility, which writes back all the results to the feature store. So then if we want to do retraining because there was a drift problem, we just relaunch the CI pipeline for the ML using a fresh set of data. And again, it's fully automated. Okay, so with that, let me move into the demo. Okay, and by the way, again, this one is documented if you go to feature store end-to-end demo, I believe. So this one, you see all the description of that demo and the actual notebooks. So the first thing that we need to do is build the features. Remember, we have the core features are built out of the swipe transaction, the credit card transaction history or live feed. So we're going to essentially that's the notebook. So I have the data set that I'm using is essentially the standard scoring data. Again, starting the project with some creation of a project, and then I open. This is some data that also you can find in the internet of credit card transactions from different users. So it includes the amount, the category, and so on, if it was a fraud or not. And what we want to do is build a feature engineering pipeline that has different manipulations on top of that input data set. So we want to extract information from that, like what was the hour of the day of the transaction, if it's day or night, what was the day of week, weekend or day. We want to do all sorts of mapping of the ages to category groups of ages. We want to do some one-hot encoding on the type of transaction. Was it buying shoes or buying some groceries? We want to run different aggregations on the data. For example, I create windowed aggregation of the sum of sum of purchases. Maybe even do the same across categories, like how many shoes you bought this month and how many groceries, and etc., or how many activities of each one of those categories you've done, and eventually you want to materialize the output into the feature store. So what we do is we just create a new feature set, which is a set of features that we're going to ingest together. We define sort of the key for the data set, and this one has a timestamp, it's transactional. And then we define our feature engineering pipeline. So this entire pipeline that I described, it will take you probably 3 months to productize it using SQLs or Spark or things like that manually. You can write it. This is the entire description of all this pipeline that I just mentioned. Have some data extractions, value mapping, encoding, aggregations, 2 sets of aggregation, and then I materialize it in 2 ways. So this is how I define the full feature engineering pipeline in order to make those features that are later on usable for training or serving. And I can just go and ingest a data frame from my own notebook to test and visualize that result. So here I can see the aggregation results and encoding results that were generated for me using that pipeline. I don't have to run it as a serverless function that listens on Kafka. I can actually build the same features and debug them locally in my notebook or my IDE and see the results. So it can iterate much faster without depending on external data engineering resources. Once it's set, I just save the feature set. It will be saved. It will be saved in the feature store. For example, the transaction. I can see the features that were generated, all the transformations, even a preview of the data, and all the statistics. So that's without any extra work. I just saved the feature set, and that's it. Let's go back to here. We can do the same for other types of streams. This is like user activities, logins, logs out, etc. Building a simpler pipeline this time, etc. And also the labels, we can build a feature set for the labels that we're going to use. At this time, we only have an offline feature set for the labels. We don't do labels in real time. And again, we created 3 different feature sets. Now we save those feature sets, and we can work with them for interactive development. At a certain point, we may want to transform them into a real-time pipeline that listens on a stream on Kafka. So in order to do that, you just fetch the feature set from the system, and you essentially deploy that feature set as a service. That service will automatically listen on the stream. We can set different configurations for that feature function, like resources that it's going to use, what kind of stream it's going to listen on, etc. But essentially, we just need to say, go and launch this feature set engineering pipeline as a service, and that will launch containers and deploy that. So you see the move from development of a feature set for the sake of interactive development into a full production. The all difference is a single line, and then we can track it in the UI and the progress and everything. So once we've done that, we want to run training. Okay, so in order to run training, we want to create a feature vector. Feature vector is a combination of features from different groups of features. They need to be joined together with also something called time traveling. So we know how to stitch them all together using the same timestamp. And then we want to train them. So we build a feature set and the feature vector. And when we can save them, we can visualize the feature vector that was generated. You see, it contains all the data from the transactions and the event activities. And then we can just go and use a built-in marketplace function for AutoML for training them. So we can run the training that will generate the model for us using the same capabilities. Once we build the model, we may want to optimize the model and reduce the set of features. So here we're using another marketplace function for auto feature selection. So we give it some parameters and rerun the function with the auto feature selection, and will produce similar accuracy with only 5 features. These are the best features that will lead to almost the same accuracy. So I don't need remember all those features that I had before. This time I can settle with only 5 and get the same accuracy. And I can rerun the training pipeline in order to generate a new model. We'll call it feature vector short or something. So again, that's for the training. And in order to run the production pipeline with the feature engineering, this time we're going to use again similar classification model. I just added some print here just to show you some small magic that happens behind the scene. Because we need to enrich the features from a feature vector, and we also want to create an ensemble, we're using a special, in the graph, we are embedding something called a feature enrichment voting ensemble router. Essentially, it automatically knows how to enrich the incoming data and build an ensemble on top of the different models. So we build this ensemble with 3 models based on using 3 different algorithms. So the topology of that graph will be, getting the event, running the enrichment and ensemble, and feeding it through 3 different models. So built a sophisticated, relatively sophisticated pipeline with essentially a few lines of code, 3-4 lines of code. Now I build a simulator that simulates my real-time pipeline. And I just feed my pipeline with with the ID of a user that I want to check if this user has a fraud or not. One thing that I added here is printing the input that goes to my model. So I want to show you that essentially what happened. Another thing that I added in the topology, I also did auto imputing. I'm telling the system that every missing value would also automatically be imputed with the mean value of that feature. How does it know the mean value of the feature? That mean value of the feature is stored in the feature store and is fetched into the model serving function for building that feature. So when I'm doing the serving here, I only provided the user ID, but the feature store essentially added the missing features, enriching them. The model itself got the feature enriched feature vector, and it actually ran 3 times because I'm doing an ensemble. And eventually I'm getting the result of the ensemble using the enriched features. So all of that sophisticated thing that will take you months of work was done using few lines of code in auto-scaling fashion, highly resilient, high performance. Deploying that thing into production is, again, just 1 line of code. Say deploy, and this thing gets deployed into a production pipeline, and I could just go and start simulating the data against the system. Again, I can build full pipelines that will essentially do, put all the things that I just showed you in an automated workflow for production. So with that, I think we're already almost out of time, and I want to try and get to address some of the questions. So, and all the information you can find in MLRun.org, and there's a lot of webinars. If you go to search MLOps Live, you'll see a lot of individual webinars on the different topics. So let me, see there's a lot of questions, so let me try and address them one by one. And if you have more questions, you can write them off. I can stay a little longer if you guys can. Okay. How does Iguazio work with SageMaker? One of the things that, again, the pipeline that we show with the CI/CD can actually launch external resources like SageMaker training or Azure ML training and so on. And also the models that you generate in SageMaker could be imported into MLRun serving graphs. There's actually a video that demonstrates how it's done, how you can actually install the MLRun SDK inside SageMaker Designer and then do all the work from SageMaker directly. SageMaker doesn't provide you the facilities as MLRun does, with a real-time pipelines, feature engineering, and auto scaling for the training and all of that. So it essentially complements each other. Okay. How does Iguazio compare to Psychoderm and Seldon? Psychoderm, as far as I understand, is more sort of a data versioning solution. It's not really doesn't do all the things that I showed you in terms of tracking the full experiments and doing the auto scaling, the serverless functions for both training and sort of the serving. Doesn't have a feature store as far as I understand. Seldon is a tool for serving, but is very minimalistic and is not serverless. So it has two downsides. One, you can't build the sophisticated pipeline that we can build with MLRun. It has far lower performance because MLRun uses a Nuclio, which is a real-time processing engine underneath with all sorts of optimization tricks. And also the MLRun serving can build complex graphs, including what I just showed you with auto feature engineering. There are other nice examples in the documentation of like NLP graphs, and you go to the serving examples. You have like NLP processing graphs. You have other examples of way more sophisticated things that you can do in Seldon. And again, you don't need to implement Docker containers and YAMLs. You just build your code and deploy, which is not something you can do in Seldon. I do compare TFX with MLRun. Again, TFX is essentially a library and containers. MLRun has all the same functionality with the integrated logging, with auto scaling, with the resource optimizations. I don't think you can really compare the two. Is MLRun integrated, compatible with SageMaker operators for EKS? So MLRun works with EKS. I'm not sure what it means, operators for EKS. So when you launch a job on MLRun, for example, let's say you're using GPUs, it knows how to work with EKS to essentially load the virtual machines with the GPUs, launch the job, and so on. So that's if you're using SageMaker and training everything using SageMaker, then MLRun will essentially launch the SageMaker work job for you after forming the data snapshot for the training set. There's a nice demo if someone wants, I can show you offline. We have something nice with Azure ML. We're essentially creating a data snapshot, launching AutoML using Azure ML, and taking the models and building a real-time ensemble off of them. Could we publish the artifacts and versioning? Everything is automatically versioned. Everything that you're doing in MLRun has versioning built in. Let's go to the project. For example, I go to models. Models are versioned, and every version has a lot of information built into it and artifacts. See, even feature sets, every feature have both tags, labels, which is more like a branch or a tag in Git, and has a commit ID. So every object in MLRun, whether it's a model, a feature, a job, a function, etc., all the time has a versioning data, and also the code is versioned alongside with the function itself. So if I go into the job, I can go and see what was the actual code that was used with that function. So everything is version, and also one of the key things that MLRun can have, you can version on a project level. So if I'm building a pipeline that has feature engineering, model serving, etc., I can make sure that they all align on the same version. It's a very tough problem in production that if you use discrete components for that, you can't really solve it without a lot of glue logic. So most of the notebooks, I think, are in GitHub, in either the MLRun demos repo or in the documentation. There's also the MLRun demos repo, which has a bunch of nice projects, deep learning, machine learning, and so on. Will the recording be shared? I assume it will. How does MLRun compare with MLflow? So MLRun has is sort of on one end distributed tracking system, and you've seen a lot of the tracking happens automatically, unlike in MLflow that you need to manually instrument. It's also MLRun is distributed, works integrated with the Kubernetes system, but also it's an orchestrator. MLflow is just tracking. MLRun will also tell, when you're telling MLRun run distributed job, it will automatically create the job and all the resources around the job and launch them. And then it will also track. So it's bi-directional. On one end, it orchestrates, on the same time, it monitors. And it has all the other pieces, model monitoring, etc., built into the same framework. So if you use MLflow, you just do the tracking of your experiments and maybe your models, but all the other pieces, you need another framework. In MLRun, you can store a model, and then just one click you serve it because you have a model object that fits into the serving framework, and one click you monitor it because the model objects store a lot of metadata that is used for the monitoring. So the nice thing is the same object are used across the entire workflow, and you don't have independent tools like in MLflow for every step. That's on that. Okay, any additional questions? Are there any model banks or models could be collaborated with other data scientists? Yes, again, so in MLRun, we have every project has all those things that you can manage at the project level. One of the things is models. And if the user is allowed to access the project, then you can seize models in other projects potentially, or features or any other asset that we're managing. So in terms of data lake, MLRun has what I mentioned before is sort of a notion of data objects and data stores. And it supports all the different data lakes, S3 and even Hadoop and Azure and file systems and NFS, etc. And what it provides is the metadata layer on top of those data sets. So you can essentially work with any type of object store or file store or data warehouse. We also have a nice collaboration with MongoDB and Snowflake and Azure and others on their data engines. So it essentially abstracts away all the complexity of the data management using objects like feature sets, feature vectors, data sets, and so on that are managed by MLRun with all their versioning, etc. So again, the MLRun supports Kafka. It actually is very powerful support for Kafka. So the serving graphs, the online engine is based on something called Nuclio, is another open source project that we promote, very popular, very widely used. And those Nuclio functions support many different types of triggering engines. So for example, Kafka is one of them, or Kinesis, or a bunch of other streaming solutions, where you can just specify what is the Kafka topic you want to listen on. It knows how to automatically load balance shards and checkpoint and recover shards and do a lot of different things around stream processing that you don't need to care about. You just provide the Kafka endpoint you're going to listen on to the same graph, and you can say on one end test it on HTTP and just tap into Kafka or Kinesis and just feed it. And again, very powerful, very high performance, and all the aspects of scaling are automatic. So first, everything that we're showing, there's a sort of a question about commercial aspects. So everything I'm showing, MLRun is open source. You can deploy it to yourself, or Helm charts and all that. But Iguazio provides a fully managed service in all the 3 clouds, as well as for on-premises on top of like VMware. So that's more of a commercial offering that comes with more security, more sort of data analytics capabilities, and so on. But you can also deploy that as an open source system. And you can install Iguazio again also as virtual machines for on-premises. We have lots of such deployments, and we have actually also lots of deployments where it's hybrid, where you have an on-premises component and also a cloud component. and works with on-premises, not just traditional VMware, but also we work with like Google Anthos and with Amazon, sort of their sort of edge solution that we're certified on top of all those things. So anyone, again, that wants more details, more demos, more documentation, just shoot me a note in LinkedIn, and I'll try and get back to you.
Okay, thank you so much, Yaron. I really appreciate that. And for those who aren't, or maybe you didn't realize, Yaron's actually in a quite a different time zone for us. And I think to say that this isn't a convenient time is a bit of an understatement. So thank you so much, Yaron, for making and taking the time. First of all. Second of all, a lot of the resources that Yaron and the folks at Iguazio have put out, such as what you've seen today, as you mentioned, is online, and it's actually fantastic. So I would encourage you all to check that out. The third thing is tomorrow, I hope you all can join us for the sessions on the platform tomorrow. There will be some more information from Iguazio, the virtual booth, and you can also reach out that way and register your interest as well. So that's an easy way to just do it with a click while you're on the platform. So just to remind you all to do that again tomorrow. But with that being said, yes, thank you, Yaron, for making yourself available. Folks, if you want to connect with him, please do so on LinkedIn. We will be editing and sending this video back with the questions and the resources to follow. And I think that's it. So I hope to see you all tomorrow. We do have one more workshop that's taking place, which you can still catch. But as well, thank you, Yaron and the team at Iguazio. They've been great partners for us for our MLOps initiatives throughout this year and last year. So we're very, very grateful and grateful for you, Yaron, for taking the time.
Sure. Thank you guys for listening.
Thanks, everyone. Please feel free to connect with us, and we'll see you again tomorrow. Take care.